Alright, so part A asks, derive an expression for the distance x in terms of h, theta, and m, and physical constraints as appropriate. So first we can start off with the range formula, which range formula gives us the distance it travels horizontally, which is x. So x is equal to vi squared sine 2 theta over g. Then we have vi squared, but we can use conservation of energy to figure out vi squared. So we know that at the point at the ramp where when the cyclist and the bike jump off the ramp, we know that potential energy mgh or mgh null, we have to null here, has to equal 1/2 mv I squared, because the potential energy has to equal kinetic energy at the point when the bike leaves the ramp. So right there. So now we can solve for vi. So we multiply 2 to both sides, which leaves us with 2m naught g h naught is equal. We divide okay, then we're left with mv I squared, divide m in both sides. We're left with 2g h naught is equal to vi squared. And then now we can just substitute the vi squared from the top into the top formula that we found. So x is equal to 2gh sine 2 theta divided by g. But then look, we can't cancel out the gravity since they're the same. Therefore, then we are left with x naught is equal to 2h naught sine 2 theta. And this is the expression we can use to find distance x. Alright, in part B, it asks derive an expression for, in part B, it asks if the vertical distance between the top of the first ramp and the launch point were 2h, null instead of h, with no other changes to the first ramp, what is the maximum number of cars that the stunt cyclist could jump over? Justify your answer using the expression you derived in part A. So in part B, so using the expression I derived in the beginning, 2h sine 2 theta. So we keep everything the same, but we only double the h. So instead of 2h, it's 4h now. 4h sine 2 theta. And if we look at it, if we double the h, then the only thing that will happen to the x would also double. So it would become 2x theta. Because, if you multiply, because over on the right side, we just multiply by 2 to double the h. And then so we have to multiply the x by 2. So it's 2x. So by doubling the height, we also double the length. So instead of 6 cars, which is shown right now, if you jump over 6 cars, it would be able to jump 12 cars. Since if we double the height, it would double the x. in part C, derive an expression for the magnitude of momentum in terms of h, theta, and in physical constraints as appropriate for when the cyclist leaves the ramp. Alright, so it asks for momentum. So we know the momentum. Here, part C. We know that momentum is equal to m times v. And in this case, it would be vi. This is asked right when it leaves the ramp. And going back to part A, we said how the energy when the cyclist leaves the ramp is mgh is equal to 1/2 mv squared. So, because of conservation of energy, 1/2 is equal to vi, specifically vi squared. And then now we just have to solve for vi. So we multiply 2 to both sides. Vi squared divide by m. And then just square root. Left with the square root 2 2h is equal to v I. Alright, sorry for the messy handwriting. And now we just have to plug it back into our momentum. So P is equal to m naught. And then just plug in our VI, which we just solved for, square root of 2 G H naught. Right. So just to recap and re-explain. So it asks for momentum, which we know is mv. And then to find v, we go back to conservation of energy. And we know from part A that the energy when it leaves the ramp is mgh is equal to 1/2 mv squared. And then we just solve for vi. Or the v squared is specifically vi. So then we just solve for vi and we just plug it back in to the top. And we're left with m square root 2gh. Alright, part D asks, derive an expression for kinetic energy peak at the top of the trajectory during jump in terms of h null, theta, and m physical constraints as appropriate. Okay, so it asks for the kinetic energy at the peak. So we know that it's part D. So we know that kinetic energy peak that's equal to 1/2 however for the v. So we know at the peak then the cyclist has reached its highest point, and whenever during projectile motion, whenever something has reached its highest point, at that instant the velocity vector it's only moving in the x direction. There's no y velocity. Therefore, we know that the velocity has to be only in the x direction, vx, not vx squared. And then we know from the previous part that vi is equal to give me a second. Yeah, we know from part C that vi is equal to square root of 2gh. And we also know from projectile motion that to find the vx of something, we just take it's just the cosine of vi. Give me a second. Yeah, the vi is just a cosine, or excuse me, to find the vx, it's just we just plug it into. It would just be the vi cosine theta is equal to the vx, the x component, which is the x component is the velocity at the peak, because since there's no y component at the peak, then now we can just Just plug everything back in. So K peak equals 2 half M V, which is really Vx, which is really just Vi cosine theta squared. Then we can break that down further. So we want to have M Vi, which is really square root of 2gh parentheses cosine theta parentheses that squared. And then now we're going to square everything, distribute the square. We're left with 1/2 2gh cosine squared theta. Alright. Then we can see that 2gh, distribute that 2 out. So then we're left with m g h cosine squared theta as k e at the peak. Alright, so mgh cosine squared theta as ke at peak. That's just to re-explain everything. We know that kinetic energy is 1/2 mv squared, and we know at the peak the velocity is only the x component, because at the peak as flat there's no y, it's not moving down at the peak. For a moment at that instant it is only moving horizontal, and there is no y component for velocity. And to find the x component of the velocity, we take initial velocity, and then we use the formula vi cosine theta is equal to vx, and then we just have to plug everything back in. So we replace vx with vi cosine theta, and then we replace the vi with the square root 2gh, which we found earlier. Once we just use algebra to simplify everything, we're left with ke peak is equal to mgh cosine squared theta. Cosine squared theta, yep. Alright, part E, derive an expression for h max in terms of h, theta, and m in physical constraints as appropriate. Alright, h max is the distance from the peak to the ground. And we can use a displacement formula for this. So h max, it's just the y distance. There's a distance in the y direction from the peak to the ground. So we can say y, or excuse me, we can use common form for this. And h max is just delta y. So vf squared minus vi squared, or vfy squared minus viy squared. This is part E is equal to 2g. Since the acceleration is just gravity, the y direction, delta y. And delta y will be our h max, what we'll be solving for. Right, vfy. In the y direction, the final velocity of in the y direction would be 0, since it hits the ground. Therefore we just cross it out, and then we're left with viy squared. And to find viy squared, we can just use one of the formulas which is vi sine theta is it vi sine theta is equal to viy. And then now we just have everything we need to solve. This is algebra now. Zoom out, get more room. All right. So vi, which we know from the previous part, is just square root of 2gh. So negative viy squared, which is vi sine theta, and vi, which we replace with square root of 2gh sine theta is equal to 2g delta y. And now all we need to do is just, oh, I forgot about the square here. So let's distribute that square. That would be equal 2gh sine squared theta. Then we got 2g delta y. Then we're going to divide the 2g over. Then we remember that gravity is negative, because gravity is negative 9.8, it moves downward. So we can cancel this 2g with this 2g, and then we can also cancel that negative. So 2g divide 2g, then we're left with h sine squared theta is equal to delta y, which is equal to h max. Alright, part F. On the axes below, sketch a graph of the vertical component Vf of the stunt cyclist velocity is blah. Then on the vertical axis, clearly indicate the initial and final velocity components in terms of h, theta, m, and physical constraints. Alright. Zoom in. Alright, so it's asking us to graph Vy, so it'll be a Vy time graph. And then we know that, since it shoots up at an angle, Vy starts positive, but then as gravity pushes it down, it slowly goes to the negative. At the end, then the graph would look like this. And from the previous parts, we know that VIY, we derived VIY as equal to 2GH VI sine theta. This is VIY, which will be positive. Then we know that at the peak, VIY would be 0. I mean, VY would be 0, since at the peak it reaches the highest point. Then the VY there's no more VY, so at the peak VY is 0, and then we can use the formula we found for H max for Vy at the peak, which we found was H sine squared theta, which we found in the previous part. And then once it reaches the peak, the gravity starts pushing the cyclist down again, which will cause gravity, which is negative acceleration gravity which pushes it down, so the velocity will go negative. The Vy velocity will go negative, which is why it goes down. And then, but it will have the same magnitude as VIY. So we can use, since it loses the gravity is 9 point, it's the same. So we can also use, because the magnitude would be the same, we can also use this 2gh sine theta for the V final VFY. I'd like to go back to part E. I'd like to go back to part E and D to clarify that it's not H is H null, and theta is also theta null. And then for part E, and then part D, same thing, M null. G is not G, H is null. Right there. That a bit more. Erase that. H is null, and then theta is also null right there. Just want to clarify that, and then go back to part C. Oh, yeah, part C, I have that. H null. Part B, clarify theta is theta null. Then part A, that theta is also theta null, right there. Alright. And then I like to zoom into part F. Let's clarify that it's H null, theta null, H null, theta null, then H null, and also theta null right there. Alright, part G. On the axes below, sketch a graph the potential energy for stunt cyclists as a function of time, blah blah blah. From one leaves a ramp to the second ramp. And then on the vertical axis, clearly indicate initial PI in terms of H, M. Take your positive. Okay, so it goes off the ramp, and then it gains height. And we know that when something gains height, it gains potential energy. So it gains potential energy until it reaches its peak. But then it falls down again, so it loses height. So we know when it loses height, it loses potential energy. So it moves down until it finally hits the ramp. So to explain, it leaves the ramp, it jumps up, gains height, so it gains potential energy, and then when it starts falling down, when it hits that peak right there, loses potential energy until when it hits the second ramp. And excuse me, based off the previous part, or excuse me, not based off. Well, after the math we've done for the previous part, we know that at the base of the ramp, the potential energy is equal to mg h null. And then at the peak, the potential energy is equal to mg h max. Right. Oh, and I like to just go back and just to reiterate that is h mgh null. All right.